Hi everyone, my name is Susmit Shannigrahi. I'm an assistant professor at Tennessee Tech. Joint work with my co-authors, Chengyu and Craig Partridge at Colorado State. So in today's network, naming at the application layer is separated from the addressing at the network layer. So in this example, we have xkcd.com/1222 and the IP address for the host ends 192.67. We can rename the content at the application layer. We can make it 1226.xkcd.com and nothing needs to change. That's not the case for NDN. The same comic strip is in NDN is probably going to be named as xkcd/1226, and there would be a forwarding entry in the network /xkcd that will allow the network to forward the interests to the data source. Now, if we change the name to 1226/xkcd, now the network state has to change. So let's say we have three comic strips, 1226 xkcd, 1227, and 1228. Now we have to announce three routes into the network. So the motivation for this work is we know that names are the central construct for most NDN operations. The way we name the data at the application layer, it affects both the application themselves, but also the network, though in the context of scientific data. So why pick scientific applications specifically? First, we have been collaborating with different scientific domains, climate, high energy physics, genomics for a long time. So we have seen how they name their data, how we can convert those names into NDN names for naming. So the questions that we want to answer in this study is that how we can create NDN names from existing names. What are the trade-offs of such names? And if we have another scientific community which wants to use NDN tomorrow, can we come up with a list of recommendations for that community so that they can? So this is the outline of this talk. So we talked about the motivation. I'm going to explain a little bit about how the existing names work in scientific communities and how we can translate them into NDN. We're also going to talk about how naming affects different NDN operations, forwarding, routing, caching, it's like that. And then finally, we're going to talk about a different few naming recommendations for the applications as well as the network operators. With these scientific communities, a few things that we found is first, these communities, they have some sort of naming schemes. They are usually hierarchical, they're community driven. So the communities themselves came up with these names. It's one thing to come up with naming schemes. Enforcement is completely separate things, separate matter. Some communities do it better than the others. The naming structure differs in different communities. So some communities, they use sort of community agreed upon namespaces. For example, in genomics, you have the tree of life, so genus, species, subspecies, and so on. In some of the communities, the namespaces are an artifact of data management. So someone came up with a scheme that makes most sense to manage their own data sets. The other thing we noted is that the files, they need to be identified as as part of a larger collection. The names themselves, they're not only hierarchical, but they are also semantically meaningful. Applications may not care about the specific um, information in the names, but the users and the scientists very much do. So though we can have a name, sort of alphanumeric string, all the scientific communities we have worked with, they have named their data in a way that allows them to identify, look at the name, and be able to tell what kind of data is in that particular file, um, maybe where it was collected, how it was generated, and so on. So let's look at a climate file. At the top, we have the original name. At the bottom, we have the translated NDN name. So at the top, the original name, of course, it has a host portion, which is this portion, the directory structure, host name followed by some sort of high-level directory structure. Then from here, we have the actual data organization. So we have CMF5, which is the organization or the project that's generating the data. We have output 1, so this is an activity within that organization that's creating the data. MIROC, which is the institute, followed by several other components that make sense for that particular community. And finally, we have the name of the actual file, which you might note repeats a lot of the previous components. So the resulting name looks like CMF5 output MIROC, MIROC4H, and followed by different components. In physics, it's exactly the similar format, though there's a subtle difference we are going to talk about. So for translating this name, it's pretty straightforward. We got rid of the host portion of the name, and everything else was pretty much the way it was before. So we didn't need to make any massive changes to the naming scheme. So we changed that, we took that name, we worked with the scientists and figured out what information we need to embed into the Indian name. It started with /biology, SRA, and then different domain-specific information that made sense to that particular scientist, to that particular community. So the takeaway from this is that regardless of which scientific communities we are talking about, there's a concept of hierarchy. Some communities have already named their data according to this hierarchy. Others, they have not, just like the SRA ID we saw, but they have some sort of community-defined hierarchy, for example, the tree of life, and we can use that to, or the communities can use those to convert their existing names into those hierarchical names. This is good news for NDN because regardless of which scientific communities we are talking about, we can probably find some sort of hierarchy that can be used to name their data. And so fine, we can name data for an NDN network, but the questions remain that if you tell scientists that yes, you can take your names and then use them in the NDN network, they're going to ask you, well, how much information should I include? What should be the order for these informations? How does the network handle these information? What are the prefixes that we should announce into the network? We divided the namespace into two different types of names. One is expressive names, which has more information for that particular community into the names. So as a result, they are more they're longer. And then you have shorter names. Those are compact, doesn't have as much information. Of course, expressive names carry more information that provides better context for both the application and the network. So in expressive versus shorter names, we have sort of a design continuum rather than the exact lengths. So expressive names, they carry more information. So they provide better context both for the network and the applications. For example, if we have a probabilistic caching, we can cache any content that has CMF5 in the name. There's a trade-off here, whether we make the names longer and make the operations, network and application operations better, or do we create compact names that results in lower overhead and smaller in network state. Okay, so I'm not going to go too much into the details of this because it'll take a long time. But essentially, for in-network operations, expressive names are better for both caching, forwarding, and routing. If we use the popularity-based caching, of course, there is no effect, but in any other type of caching, expressive names are better. For forwarding, it provides a fine-grained forwarding plane. So if you have two subcomponents and you announce both of those into the network can give you more granular forwarding based on the longer names. And that doesn't happen with the shorter names. The shorter names, on the other hand, they're potentially faster because it takes less time to parse them and process them. And also they create less state in the network. If we look at the data structures in NDN, once you have the expressive names, the interest and the data packets interest packets become larger, and the data packet, they have less space for the payloads. For FIB and RIB, of course, expressive names mean they're going to be larger compared to the shorter names. So the example we have here is genus, species, subspecies. So if you're announcing 3 subspecies into the network, your FIB is going to be larger than just announcing /genus. But that gives you more, announcing more routes into the network gives you more control of how you can forward the packets. Let's look at publication. If we want to do partial replication, so genus, species 1, subspecies being announced from one source, genus, species 2, subspecies being announced from another source. We must have partial names, because if we only announce /genus, that does not support that partial namespace replication. So in these cases, we can use forwarding hints to take the request to that particular host that has those sub namespaces. For data discovery, more context is always better, both for indexing, discovery, and search. The downside is the privacy. We expose more information with longer names. What did we learn from here? The expressive names are better suited both for network operations and applications. The trade-offs are smaller payload and larger in network state. Which ones should the communities prefer? It depends on the application and the network operators. Our job in this work is only to point out the trade-offs. So we finish this off by introducing the concept of minimal usable data units, or MDUs. So in scientific communities, a set of files are often used together. Single files are pretty useless. So on the right, you will see a bunch of genomics files, and they are always going to be used together. Um, you cannot take, for example, the file at the bottom and then hope to run some sort of computation. So in the context of scientific networks, it makes sense to treat all these files as a single entity. The interest and data packets should handle them consistently. So for example, uh, use the same upstream and downstream for these files, the same strategies. They should be cached and evicted together. And then subsequent requests for these, since the data is large, they should be sent past that cache. Note that we are not proposing prefetching with this idea. All we are saying is that since all these data sets, all these files, they are always going to be used together, it makes sense for the network to be cognizant of that fact. There should be sort of a hint at the network layer that, hey, file 1.5 is coming in. That means all these other files are also probably be requested. And they should be handled in a particular way. How this should be implemented, it's a research question. It can be implemented as a strategy. What kind of handling makes sense? We don't know the answers to those. Hopefully in a future work, we will be able to address that. Going back to our initial goal, that if another scientific community wants to come in tomorrow and use NDN, how should they name their data? So here are a few pointers. The names should be constructed using well-defined, hierarchical, human-readable, and semantically meaningful components, because those provide more context to the users, applications, and the network operators. Longer names are more useful. The trade-off is space. One option is to use linked object to have two names for the same object. You can have both shorter and longer name. Things are named today, host name followed by directory structure followed by file name. It may be very tempting to replicate that name into an NDN namespace. That's not a very good idea. So if the location information is not needed, it's best to avoid including that information in the name. The name should be identifiable as part of the MDUs. For larger namespaces, the use of forwarding hints might save a lot of networks in network space. So the community should consider that. Any sensitive information should be put towards the end of the name and then encrypted so that the routing functionality and the forwarding functionality is not affected by that encrypted portion of the name. The recommendations for science network operators, the shorter names generally, I know it depends on the implementation, but generally faster. But expressive names help with everything else, caching, forwarding, things like that. Again, data names should be location agnostic. So CMF5 CSU is much easier to handle in NDN than /CSU/CMF5, unless you need to know the location. So if you have, for example, two data sources that you're load balancing between, you want to uniquely identify which endpoint your data is coming from. Otherwise, there's a chance that you might load balance in the network, but all the requests would end up at the same source. The operators should also look into caching and forwarding the MDUs together for better efficiency. But as I said, we don't yet know how that can be accomplished, or so this is still an open research question. So just to conclude, the naming is the central construct for NDN. Efficient naming that can align name data with application requirements and the network. For science data, we define the concept of MDU. It's a hint at the network layer that says, well, this set of files should be handled together. And we think it benefits both the applications and the network. And then finally, we provided a list of recommendations for the communities, but how the individual communities handle their names, it's up to the name and the network operators that are carrying the traffic. Okay, so that's everything I had. Thank you very much for listening, and I am happy to take questions. Thank you.